boy. Timing analysis failed due to the presence of combinational loops. Especially with timing ports, etc. Etc., huh? Oh boy. Timing budgets of 25 megahertz. This is not going to be a problem. It should run fine. Timing combinatorial loopage. What did I do wrong? Bus out is true. If so, send out my D out. Otherwise, send it to high. It's not obvious that that would be a loop. Okay, maybe one of these other guys is. So this one here. Oh. You don't want to do that. There we go. It should have actually been okay, I think. Is that it? I'd like for the answer to be yes. Okay, so this is just broken. There ought to be something going on up in here. Unmatched constraint S2N. That's switch 2 on the board. We don't use that one. That's the only warning. So there's an error. We have an error, but it doesn't bother. Oh, it's in caps. Due to the presence of combinatorial loops. Incomplete spec of timing ports. Wow. I hate when that happens. It's running PNR. That's interesting. So IOSIS didn't care. It's PNR. Make world. What is it? Dink less. Did I get an error anywhere else? No. There we go. Dbus out is assigned in a block at 93 and 95. Assigned a block at 98 and 99. Dbus out is an identifier SSEL is implicitly declared. So that's obviously bad, no matter what. Dbus out being assigned multiple times is okay, provided that they're not in different blocks. So let's see what's going on here. Well, let's get rid of the SSEL first. I'm wondering now if the giant always block would have been okay to IOSIS. I don't know, because I did read the manual and it said it's limited to this format, but it might have been that they updated it sometime. And I don't. Oops. And I may have missed. That may not be a constraint that it still needs. Come on, damn it. Jeez. Okay. The hell is it griping about? It's on line 93. Okay, dbus out is 0. Who cares? This is perfectly fine in a purely combinational block, which this obviously is. So I gotta wonder if, like, SSE, what was the other thing it said was not defined? SSEL is obviously broken. Let's get rid of that one first. Oh, because it's active low. And it's actually okay that this is upside down, because it's upside down in the code as well, in the BIOS code. You suck. Okay. Alright, it's still peeved off. Okay, so dbus out is assigned a block at 93, 96, 99. 93, 4, 5, 6, and 99. What did I forget here? Well, this is true. Sign that. Otherwise, if some other junk is true, do this. Wow. I don't see it. What did I do wrong? Oh, this is so stupid. World's stupidest error message. Oh my God. Oh, dear God. Okay, yeah, you assigned to regs from inside here, not to wires. You stink. That warning is just ass. Okay, that's the only one. Normal. Yes. Fine. Whoa. Now what? You still reek. Boy, that's a tough one. Timing analysis failed. So does it say anything here? 25 megahertz, blah, 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 yada, driver. Specification of timing ports. Okay, so what might happen... jeez. Is in here... Where did I do the 25 megahertz? I grab 25 from star. So what I did is I told it, grab 25. Somewhere, maybe in like make rules or something. There's like a timing constraint. I thought I put it in somewhere. 2057 rules, make rules. When you run this thing, you can tell it that you want it to be able to generate code that will you want to verify that it'll go at least 25 megahertz. So what happens is, I remember playing around with that. I can't see the number 25 anywhere. Right here. The budget for 25 megahertz. Somewhere I configured this thing to say, make sure that nothing takes longer than, here it is, freak 25. So why is there not a 25 in a file somewhere? Did I miss it? Grep 25. Here we go. Grep recursively. First, let's clean. There's been all the junk files everywhere. Grep minus R 25 from here. Can I just clean the whole tree? Grep minus R 25. Where the heck is that dang thing? Hardware clock. Why is there crap in the SRAM? Make clean. Because I didn't add those to the other build. Make files yet. So some idiot here and make rules. Set this. Now, when I say freak equals that, in my make rules, what might be happening is that the analysis that goes on in placing and routing, this is where the timing is you know, of concern. Well, where does all this stuff go? How long should the wires be? What happens is, if it can't figure out what I'm using as clocks, it might not be able to do the job, and the error message could just totally reek, or I have some other mistake in my code. So what I'm going to do is I'm going to comment this out, and then I'm going to take this freak out of here, because if I don't, if I don't have it in there, maybe it doesn't care. But if I do have it in there, I might have to go out and make sure, or not, that I have done enough for it to know what to do, well, how to calculate the timing. So that's not it. Oh boy. Combinational loop, huh? This is what happens when you don't run simulation first. And this is really not set up for it, because it's directly, you know, mapping these to hardware pins and I don't know. We probably could simulate this whole thing, since I'm using an inferred RAM. It'd be interesting to see how the simulation does with that memory block and everything. You know, because we could generate, you know, signals like you would from a Z8S180 and then have it doing the right thing with turning on and off the various bits and stuff. Control its outputs. Alright, so SD, Mosey, clock, SS. Did I make those wires by any chance? Yes. Okay, so these are wires, and you can assign a wire with a sign. What did I do? Come on. Are those GPIOs wrong? What's wrong? Where did the GPIO go? So that's a reg, and I assign it from here on an edge-triggered input signal like that. And it's exactly what I did up here. So that shouldn't be causing this kind of a problem. And my point is, this is not using any obvious clock. If we were using the hardware clock everywhere, the synthesis tools would be smarter about knowing that this flip-flop has a clock that is, you know, like a global buffered clock and stuff. It tries to figure that stuff out when it runs. But here I've got edges on random signals that come from combinational circuits and stuff like that, and it could be getting confused. So I wonder if these expressions are dumb in some way. F0, F1, and he wants to be, well, let's just start commenting crap. Let's pretend I'm a student. Delete stuff until it starts working. I mean, there's a lot to this line of reasoning. Okay, that doesn't do it. So that theory is bye-bye. Let's delete more stuff. Now it'll say something like, oh, nobody assigned a value to that output. Wow. So if I don't do any of this, Now, anybody that uses F0 and F1 are a problem, which I think comes in up here. Yes. I wonder if this is the... it's got to be this one. There's no other reason for it, you know? I don't know. This thing is a pain in the butt. Jeez. What else did I do? Jeez. Assign D equals D bus out. When that's true, go to D out. Otherwise, go high Z. That's okay. These are regs that get assigned values in here. If MREC N is true, and I'm reading from memory, this is the same thing. Come on. D out equals ROM data. Well, what exactly is ROM data? It's a wire, so that works. In the context of this assignment, should be fine. D bus out equals 1. Jeez. I'm just, I don't know. Basically, this is the original program now. And it should say that you didn't assign anything. Okay. Fine. This thing is just going to kill me. It's killing me. Here I thought I'd be done by lunch. Yeah, well, you gotta have goals. Alrighty then. Alright, so it's not this down here, which I didn't think it would be. Of course, I didn't think it would be this either. So what's wrong with this idiocy up here? Combinatorial loop. Is there something wrong with how I define that? Reg 70 blah. A has 20 bits. I wonder. I might have to say, which bits of A in here. That's interesting. This did work. Wherever I stole that from. Wait a minute. Yeah, I stole it from up here. That means it has to have zeros at the top because this will be, it'll be extended. So this actually could be troublesome. During a memory operation, this is fine because the higher order bits are not set, but this could have junk in there. This is a different problem waiting to happen. We only care about those bits. We might as well also put this, well, no, we do care about all the bits because if we actually turned on the MMU and stuff, then those higher order bits would be in play, and this only maps over the bottom 64K, so that's okay. No, it's not. These are I/O ports. I don't know what I'm thinking. Thinking about the guy up here. This is not right. These are all going to be 8-bit, like that. But this should still compile with the same error we had before. Okay. Alright, so this here is our problem. Where's your problem? So the original real trouble, the errors were down below. And then I started hacking this up because I thought this might have something to do with it. So if that I wonder... No. Oh, wow. Dbus out equals that, or it floats. D out D out does not have, okay, D out was not assigned anything in here. So it needed a latch. That's bad. Maybe that's what it was upset about. These errors are really, the error messages are really bad, if that's what it is. But you see what I did here? See, I only set D out, or the D out, a value when I had a reason for it to go out this port. Otherwise, I did not. So this thing had to have an inferred latch. It may have been griping about having to have an inferred latch for D out, which that'd be the world's most annoying error message. Wow. I'll see you in the Discord when you're debugging one of those. That is bad. Now, on the other hand, it does go to argue a lot in favor of doing a test bench for this blasted thing. Because if I ran a test bench, I would have seen this doing stupid things. Okay, so that's just me being a lazy oaf. All right, okay, my bad. Guilty. I have no idea what state I'm in right now. What did I just do? I forgot what I was working on. We have this thing copied over. And it has commented out the good stuff. Where am I? I'm in S180. Okay, here we go. I got to go over here. No, what I really should do is run it again the way it is. Because what this is going to do right now... Okay. I have it commented out. I don't call the SD card. Okay. I should be able to do that now. I do not do the memory copy bank stuff. So what happens is, when it's done booting, what it will do is it'll jump up to the high memory. It'll start running the code, but the bottom 4K will be stuck in the flash ROM mode because I don't yet support this disabling thing. And then CPM will start trying to get itself all set up, and it won't be able to write into low memory, and eventually it'll do something and use the low memory, and then it will crash. In fact, what it will do is it'll try to use the disk buffer down there, and it'll get garbage data. It's not like it'll catch on fire or anything. So what will it do? We'll at least see it get to the point where it will read the MBR and do some stuff. And I don't even have a card plugged into it right now. So what it will do is it will say, I can't read the card. That is a perfectly valid test as far as I'm concerned. Okay, let's go ahead now and make this again. Make world, because we got to go get the new ROM again from over the hill. Is that what it did? I mean, I can't. Make minus P. What? I said minus P. Oh, dang it. Make clean. Make minus N. All right. Fine. So it's going to copy over that, and it's going to redo that. Okay, because I got to remember to recompile this. It won't automatically recompile the firmware. unless I go in this other window over there and do it. Okay, so here we go. Make probe. Oh, I don't know. I'm afraid to even try. Where's my terminal? All right, there's really not much to look at on the bench because all it's going to do is try to reboot, and the LEDs might go on or something. It won't do much, actually, because the LEDs are hooked up to that memory write thing, and it doesn't do a squat. So what did it do? It did not boot because it needs to be reset. Alrighty, cannot read this. It is not idle. That's exactly what it should do. If there's no card in there. I should have put code in there to check the detection line and all that fun stuff, but I did not. Now I could just go find some junk SD card and see what happens. Alrighty, here we go. Let's see what happens if we put the SD card in there. Now this has a SD card connector right there. Put this on here. Now I don't know what's on that card. It's a blank card sitting in a pile of things with SD cards. Let us reboot. All right. So, boy, this could be any one of like a million things. Oh boy, oh boy, oh boy. Let's reseat the card. Now, if I look close in there, I don't see any like flux. It's not like there's goo all over it or anything. I don't see anything wrong with the soldering, really obvious. Never use the SD. Oh, that actually looks like it's a pretty good soldering job. I say so myself. One of the best ones I've done, which may be hiding something. It looks great, so I'm just inclined to say, oh, there's nothing wrong. Let me look closer. No, it's okay. Maybe there's a hair in there. You know, I mean, it could be. It's not, you know, or look this stupid. Spend 6 hours debugging something only to find out it's like I had the card in upside down or something. No, that's the way that goes in there. All right, one more try before we give up. Oh, this totally stinks. All right. So what then really is going on here? Well, the CPU is going a whole lot faster than the retro. Yeah, it's only running at 6 point what odd megahertz, but each instruction runs in half the time. And the timing on like reset the SD card and then wait a little while and then do something else, all that was based on spin loops in my Z80. It could be that this works perfectly fine. It's just going too fast. That's my story, and I'm sticking to it. So, what are we going to do about this? All right, so first things first. We need to make sure that when we read from our GPIO port that it's actually working. And we have this extra user button right here. And we have only 3 bits out of all the stuff that we're reading from the card, or 2 bits or whatever it is. Why don't we put this switch in there and then write a little, it will hack the firmware to just print out whatever the GPIO input port has on it. Wait a minute. I moved the ports. No, that's actually okay because it's got the new IO file. Where am I? All right, come on. Where are we at? Well, we can put the scope on the SD card and see if the bits are twiddling, which would be, is the clock going? I mean, is it really doing much over there? What's it actually doing with the out cache and the... Ooh. That's interesting. We never do that either. That's interesting. It may be that we are not initializing the ports in the way... Oh... We might need to do this. I don't remember whether this was truly necessary or not, but this was a part of the deal. Originally, I mean, I'm thinking about it. It may have to do with, I got to make sure. Well, I know I have to make sure I had the right RAM block set, right? The bank. We don't have banking, but we do have SD cards. So it might be that the SD card select line was in a weird place after reset. That's possible. Because the code for the SD card might use the cached value as its current value and modify it from there and put it back. And it might have been in a state where it never was in the right state to begin with and stayed that way forever. Let's just try this real fast. While we're in the neighborhood, what do I got to do? Now I have to recompile this one, and then I got to redo the program. No warnings, no runs, no hits, no errors. All right, let me hit reset button. Okay, that didn't seem to help at all, did it? All right, let's see what else I did stupid. Did I just mangle the code? Let's see, it says can't read, command 0, not idle. Who knows, the card could be bad, but I doubt it. I mean, I just grabbed a random one out of a box. Does the boot message, it goes in here, comes back and does that. So in the boot SD, it might help if I read some of the doc in here. Sanity check, the partition type and size. That's a to-do. If it should fail, then this function will return. Okay, so it said booting partition 1. Yes, it did. The response byte should be that. And it comes down, so I crap out right here. Okay. So right out of the gate, I can't do a command 0. Because this is not idle, not valid, and so on. What am I missing? Come on, somebody out there. If this was live, people would be, do this. Oh. What does this do? That sends the leader clocks, that's right. Then it tries to read back and get to status. So, if we look at SD boot and SD command 0, which is in the regular old library, as of this, it can be tested on house brand cards that I bought here. Warning, 3.3 only. Must do a pull-up. Ooh. That might have something to do with it. Okay, did I put a pull-up in there? No. All Alrighty then. You know, this is really good that I decided to take a moment to read the doc. Okay, let's have a look-see at MISO and see whether it's high or low. MISO. That's on LT181. It's also possible that I didn't, I might have got the wrong pin numbers. IoT181, where is that? Down here, right? So IoT181, on the silk screen I have the pin numbers. These are the function names. It's a little annoying that we have two different names for each pin, but I mean it's because the packages are different. These are the same, but the package pins are different depending on whether it's ball grid and stuff like that. So, I mean, I understand why they do it, but it's just so annoying. So, IoT 181 is on pin 121. Okay. Now, if we go over here, first thing we want to do is make sure that not here, it's in the PCF, right? In the FPGA code. MISO 121. 181 goes to 121. Okay. All right, that checks out. And we need to know where the 121 is so we can know what pin to put the probe on for the scope. So let's go ahead and scope that thing. Pin 39. Okay, so I put the probe on there right now, and it is at ground. Therefore, it is being driven low, or it is floating, and it's low. And master in is an input in the FPGA. Therefore, it cannot be driven by the FPGA unless I coded the top level file wrong. Okay. There is no pull-up on there. Okay. Now, it turns out that IOSIS does allow you to put a pull-up in here like this. Maybe we should pull it up. Now, these are not strong pull-ups, but they're better than nothing at all. We may find out that we have to put like a 1K ohm or something in there and pull it up on the circuit board. What else might need pulling up, okay? SD detect. It needs a pull-up on here too, but I don't know if it needs me to do this in the FPGA. I don't remember if I have a one in the design or not. I might have put one. Baby, yeah, no. I already talked about that. Yeah. Okay. Very good. Let's try seeing what happens now. This is why these videos take forever to record. So even when I know what I'm doing, it turns out to be a giant fiasco. And I do admit that not knowing what I'm doing today. That's not, I didn't mean that. So, all right. So what happened this time? Did it even say anything? I hit reset it. It wasn't watching the screen. Okay, now the scope The scope on this is ping 40. My screen captures is now high, so the pull-up works. That's good. Let me just single trace this. Alright, it never triggered the scope. There's another clue. It never triggered. Let me hit reset again. Sure. Okay, that's definitely a clue. Well, that's a... yeah, That means no one ever touched it. Nobody ever touched it. Let's do this. Oops. So I don't know if it's the I got an IO operation, one of these expressions is bad, or it could be anything. Okay, write, what am I doing? Write to F1. Write IO request. M1 is high, which means it's doing the dance of this guy down here. M1 is high because that's active high. IO request is low. And write request is low. Write IO not interrupt. Acknowledge. And the low part of the address bus has an F1 in it. Then this is true. When that is true, what's happening is this will go up, and then at the end of the cycle it goes down. At that point, I latch onto what's on the D input bus. Why don't we also spew it over to the LEDs? So we can see if anything ever happens. Alright, so let's get rid of this. And the line of code that says put the LEDs on, put the FFF onto the LEDs. What I'm going to do is I'm going to go ahead and put this down here and say it equals GPIO out. That way, if anybody ever writes anything to GPIO out, display the current. Now remember, this is the LEDs are inverted, so what I'm going to do is I'm going to put a tilde in here. That way, the lights are on if it's high, and the lights are off if it's 0. Because remember, the LEDs are wired up to light up when there's a 0 on the output of the FPGA. So that's what this will do. Right? Is that all fine and dandy? Okay. We know that the RAM must be working because when we were spinning around and calling subroutines, it used the stack. And if the RAM did not work correctly, then that would have failed. I mean, we're doing a huge amount of code in order to just print this stuff out. It's calling subroutines and spin loops, and it is ready, the console. This is doing a lot. So it's interacting with RAM for sure. Cannot read SD card. Blah, blah, blah. Remind me, where do we initialize the stack in this code? Because we cannot initialize it in the flash area. Tell me I hard-coded it up high. Ooh. How does this work at all? Wow. Where is that? Oh, it is up high. Okay, it's up at load base. That is up high. I was wondering if it was like, at 1K or something. No, it's way up high. It's at C000, which is in the RAM. Anyway, the RAM is working. That would prove that. Like, what else could be going wrong at this point? It goes into S-boot, runs to completion, and comes back. In order to go in here, run until something happens and comes back. In order to then call this and stop. So we're in and out of the RAM for managing this stack. Oh. Oh, this is great. Who figured it out? Oh, man. Okay. See if you can... The problem is we have to do this. Why do we need to do that? Because if you remember how these routines work, these routines... And even these down here, you see where it has GPIO cache? These are bytes that are sitting in memory. And they're sitting in memory that are low addresses. So no one can ever change the value of this byte because it's in the FPGA ROM code. So no one ever can change the lines going to the FD card because they're always using this to do it. There's also variables that are just DBs all over the place in these routines. And all that has to be in the boot flash, the ROM part of the code, and none of it can ever be modified. So none of the SD card stuff, it's not possible that can work. And we can even look at it right now in here. I never really did check this. The fact that the binary only has 2.5K in it means that the whole image is under 4K, which fits in our 4K implied RAM, okay? And that means it's read-only memory in the FPGA, every byte in all this code, from the beginning all the way up to 0971, okay? 1000 in hex is 4K. So we're just over halfway, just over 2K. So this byte right here that we want to be able to, load and store data into and see it change over the course of time at address 970, which is below the 1000, address cutoff, where the RAM is, can never be modified. And if you go in here, you'll see all sorts of stuff in the SD routines. If you remember back to the way we did all this, it needed working storage areas for various, values. So here, SPI write string, SPI done, read write, blah, blah, blah. In here, there's little buffers. Come on. I know they're there. There's the bit banging. There's the bit banger. I think it's the SD card that had all the weirdness with the that's all SPI. That's all actually probably okay. Then we have up here, I know we have storage areas in here somewhere. Come on. There's that. Where are they? I know we had them. There was little buffers. It had to be able to construct a command and then send the command. Read 8, blah, blah, blah. There's your local labels. I'm just looking over here for labels on stuff. There you go. What happens is we modify these messages in here. We put block numbers in there and stuff like that, and then we write them out. Now, I don't know if this particular one has that, but I know that is the case. Command 55, okay? If you look in here, it probably says load, buff, len, do this, do that. Somewhere in some of these, we have to modify these before we send them out. And thus is our problem. I'll leave that as a test for the viewer. This is screwed up. We need to turn off the ROM. We need to do the LDIR copy and all that fun stuff. Okay, so as it is right now, because the ROM kicks in and gives data on the data bus whenever there's a read cycle, and the write cycle, it completely ignores it and throws it all away. No, I don't care. I don't do anything. What we need to do is make sure that the write cycle will enable the SRAM. You know what? It probably does. This code is like so close. The RAM, what is it? Okay, all right. No, it does not. The only way we enable the only way that we enable the static RAM is if we have a memory cycle with a large address. Okay, we can change this to say the only time we want to access memory, there's a memory cycle and we are not running dbus out. If dbus out is true, we're supplying the data in here. And in here, it will do this if it's, under the RAM start. So we'll have to fix two different things. But what will happen is, if I use this, instead of putting this in here, what that means is that when there is an address less than RAM start, and it is not a read cycle, even if it is a memory cycle, it won't do this. Therefore, dbus out won't get set. It's not going to be in an IO rec cycle, so that'll come out down here. Dbus out will be off. And if I do that, then I can allow this static RAM chip to be enabled. That will give me part of the logic that's up here, which is half of the game plan, right? Remember what happens is we only allow the reading to come from the flash when the flash is enabled. But writing goes into the SRAM in this original design. You always can write into the SRAM and whatever the selected block is. And we do that so that we can, while we're booting, we're reading from the flash. If we write into the same address, it'll get stored. That's how we copy the flash into the SRAM. So I just have to change how I decide when not to allow the SRAM to function. So this new code solve the problem for us. Do not engage the SRAM if dbus out is true, okay? This will decide who gets to do it. Now we need to make sure that dbus true is reasonable, because dbus out is true when mrec and read is active and the address is low. In other words, I don't want this glitching like crazy. So you have to make sure that I could actually put an else in here and say else turn on the static RAM, and then I would have a much more graceful set of logic. I wouldn't be counting on the Z80 not to be jittering its read and write signals and things. But I think for a quick hack, we can do that. Let me think about this. If I have mrac and dbus out is not on, then allow the static RAM to go. That could glitch a little, but I don't think it's going to be too bad. If it does at all, because the write line, as you saw in the timing earlier, the write signal goes active in a narrower window than the read line does. So what happens is read goes active before write. So this will assert the D out true before someone else who has mrec and write enable and stuff like that involved in its select logic would even have a chance to say, oh, it's my turn, okay? Now, I can go ahead and enable the SRAM. I can leave it enabled all day, as long as the write enable doesn't go true at a weird time. So look what happens down here. The write enable on the SRAM is low, true, when MREC and write are low. That's a pretty narrow window. It's narrower than the period of time that the D out will be true. So I can say enable the chip if I'm in a memory cycle and I'm not in a and I'm not stealing data from the inside flash logic, because otherwise I would just say CEN is true anytime the memory is on. Period. If we do this, then the reading comes from the boot ROM, the writing goes into the RAM. For as long as, we're doing that. That'll allow this LDIR to complete and do the right thing. Okay? Now, this flash disable stuff. What we need to do for that is put another latch over here somewhere to stop this dbus out fun and games. So let's look and see up here. Dbus out is true when we're accessing low RAM. What we can do is add one more latch. We can call it reg. What did we call the signal over here? See where it says flash cell. These are really this signal over here. Flash MREC means that the flash can go on and I'm in a memory cycle. So what we need to know, what we're dealing with here is this D out thing right now is the flash MREC. What we need to do is back up and decide this one. All right? That way we can just simply say, from now on, no longer allow this to be true. That's what this flip-flop does over here. Once this thing becomes false, which is high in this circuit, it can never access the flash again, and all reads and writes and reads go to the SRAM over here. Okay, so we need a little more of that in order to do the memory copy, right? So let's go ahead and call this thing flash cell or ROM cell. That's what we called it in here. Okay, ROM cell. When will that be true? That will be true unless someone touches a port at this address here. Okay. True from reset until IO operation to whatever flash disable was set to. Is that F2 probably? Lib IO star 70. Wrong library. Lib nouveau, blah, blah, blah. Flash cell. Okay, FE. O1 and FE. Okay, so all right, so what are we going to do? This is like having it set in an initial block. And if FPGA will let you do that, when the FPGA resets itself, that will be true. This is not what we want. What we want to do, we want, whenever the reset button is pressed, because this is fine when you first power up the FPGA, but if I hit the reset button on my board, I needed to reset that ROM cell. Okay, so the reset. I think we're on the home stretch here, people. And there'll be another fiasco after this, I'm sure. Okay, let's see what's going on. We got to keep this. Got to keep us on our toes. So reset, and what I'm going to do always are we going to actually do? Whenever reset N goes high, we want to remember. So what we can do here, what we need is to just always look at it. We want to say if reset N is true, then we want to say ROM cell is a 1. Right? And reset N is upside down, so whenever that is true, do this. And do I then do this? ROM cell equals 0. What we need is an RS latch. But I was thinking of this. Is it HW clock? Yeah, oh. Phi will do, I am sure. You need a free running clock so that it comes in here all the time. Anytime there's a clock and reset is low, we set ROM cell to 1. Oh, it has to stay. Oh boy. Oh, okay. That's not what we got. No. We need to do something here. We need a little state machine. And this file is just filling up with so much crap. Well, we're going to get there. What do we need to do here, right? So what we have here is ROM cell. I'm going to just say a ROM cell next. Okay, and I'll put this down here. Okay, so the way this is going to work is ROM cell, he goes true there, otherwise it equals next. Okay, now inside here, we're going to say that ROM cell next always equals what? 0. In other words, don't use the flash anymore. Is that true? We have a state. What we have is what do we have? We have a state. It's so simple I can't visualize it. We need literally an RS latch, but there is no well, actually I guess there is. You could list both the reset and the whatever is the I don't need a reset anymore signal. What we have is when this is poked at, whenever the flash disable is accessed. So when this is running, I see. If flash disable is ever active, and because the IO port is being accessed, we'll create another one of these down here where we have all these little decoders. So it'll be like IO request. It'll be read FE. We'll put a little comment here. This is the flash select disable access port. Alright, this is the GPIO output. This is the GPIO input. Okay, now the FE will go active just like this one does when reading. A different address. It's reading and yada yada yada, and we're going to go to FE. We still don't really know for sure that this is working, but I do know that we can't do anything if we don't have RAM in the low addresses. And there's many ways to fix that. We can just move the data up high. I don't want to deal with that. I don't want to redesign the program, which would be another way to do it. It's not a big deal, but I don't want to hack that code. It's pointless. We got to get through this eventually anyway. I thought I could hack it. No. We have to do the whole thing. All right, where am I? If this, which, by the way, after all the other problems we've had, I'm pretty sure you can assign them right out of the gate with these things. So what I'm going to do here We'll do that later. I don't care. Grabbing at straws earlier left me in a weird state. FE. Okay, so what am I going to say? If this is ever true, if I'm in ROM cell mode and FE goes true, then the next ROM cell is going to be 0. Okay? Else, well, we can actually just do it like this. There we go. No. No. Oh, I'm getting punchy. Oh, this is just ass. Okay, don't change it. So I have an implied latch, an explicitly implied latch there. Else, nothing. Yes. Okay, the next is what it is now. Whatever that might be. If someone is touching and diddling with FE, then I want to shut it off. And as long as the IO logic that this is active longer than one, long enough for one pos edge to show up on the feed clock, which it definitely is, then this will run on that edge and it'll say if someone's hitting the reset button, we want to turn ROM cell on. Otherwise, set ROM cell to what this guy down here says. And this is a 2 always block state machine. We just talked about this on the channel. So, yeah, whenever this thing gets popped, turn it off. Otherwise, leave it on. I don't really need this here. At any time, if it's already 0 and I set it to 0, it can stay at 0, so we don't need this logic. It'll figure this out probably on its own anyway when it does its design analysis during synthesis. Next is current. IOREC FD is on, then turn it off. I can just put this all in here, by the way, and make a single always block state machine if I wanted to. Somebody's talking to me about that on the Discord. So if you really wanted to do that, you could easily do this and say that ROM cell becomes 0 here. Else, I'm pretty sure this will work, right? ROM cell. What I actually need to do is not touch it. If reset is true, do this. Otherwise, if that is true, set it to 0. And if I'm not in reset and I'm not touching the port, hands off, leave it alone. And that's your 1-bit memory. This would go away. This would go away too. And that's the wiggler. There's one for the wiggler. Right. Clock's going. I saw a reset. Make it a 1. It's not reset, but somebody's diddling with the FE port. Shut it off to 0. Not doing anything at all. Leave it alone. Okay, now we have the ROM cell, which matches this here. This up here, by design, this is simply the inverse of the other one. These just flip back and forth. So I have those signals now. So now I know when the ROM is supposed to be on. So now I can use that. Where's my D out fun? I could play around up here, but I don't think that's what I want to do. I think I want to play around down here. I want to say if... Yeah, if that's true, that's true. If MREC, I could probably now simply say if ROM cell and that. So I'm supposed to select the ROM, and I'm going to select the ROM. Go for it. If ROM cell is false, then I don't want to do the ROM anyway. And I still have to check to see if I want to do an I/O operation. That's fine. That probably is good. Well, now it's ugly enough that you really want to have a test case for this. I mean, it's just, no. This is me being an idiot. All right, here we go. Wow. Died right away. Not anything. Oh, well, you know. I'll let that one happen. Okay, here we go. Let's space that out, because, you know, that's an error if you don't get your spacing right. Okay. All right. Any last requests? What did I forget? I don't know. While talking, I can't keep track of anything. All right, here we go. Keep all this highlighted so we can see if anything happens and changes. It's programming. It's going. I should do something so it automatically resets the CPU after programming. Ooh, the LEDs lit up and did something. Am I capturing the camera? Yes. All right, so this failed, but the LEDs are on now. I don't really know what it means, but, but they're on. And it's symmetric. So I don't have to remember which one is bit 0 and which one is bit 7. So what do we got? We got triple on, and then 2 off, and then 3 on again. And that would be in the firmware. That was written to GPIO out. Because he writes this value in there. So that should be all right. E is 1110. That's why I've got 1110 on one end of the LED register. And these over here are the other 3. And they're what? I guess they're all right next to each other, bunched up in this register down here. And those are the low order 3 bits. So that makes sense. So I got all these are high. And I can see that what would be the low bank thing is also high. And the other 2 bits in this sequence of things are all zeros. Assuming, of course, that these are assigned bit, you know, like 1, 2, and 4 in terms of their values, like their binary values. What am I looking at here? And they should be, right? IO in and a flash disable. 1, 2, 4. Okay, perfect. Okay. Well, now what I'm going to do, I know that we can write to these things. I'm going to change the LEDs, and I'm going to write these bits, because we don't care about the RAM flashbang crap. We're going to put those in there. Then I'm going to also put these in there. So I'm going to put these in the most significant 2 bits. I'll put the SD detect and meso on the most significant bits. Then we can see if I take the card in and out and stuff like that, that the light goes on and off so that that signal is working correctly. I also need to clip the scope on there and turn that back on to see if I'm getting any action on the clock or the chip enable and stuff like that. I suppose I could do that. No, let's do the LED thing first. And what we want to see there is, all right, instead of just saying GPIO out, what I'll do for that is I want to see the low order 4 bits of GPIO out. So that will be one of these concatenated dealies. Okay. Oop. What am I? 3 bits. 2, 1, and 0. 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 2, Okay. Then I want to see the SD card and all that fun stuff. They have signals around here somewhere. No, actually, that's the input value when it says, I want to see, it's right here. It's 2 bits followed by a bunch of these, and that makes meso the most significant bit. It's possible that I got the ordering wrong on these or something. Meso is the high bit, and det is one next to it. So there should be like 8 whatever, 80 and 40 in the config file. 8040. Okay, all this jives, good enough. So what I want to do is I want to take these 2 values and add them to the LEDs so I can watch that as well. And I mean, it'll be going so fast I can't really see. And then there'll be 2 bits of, I'll put 1s in there, so the LEDs will then be off. These need to be inverted, otherwise the LEDs will be backwards. Fine, so the detect should light up the LED. Yes, and meso is true when the LED is on. And these are also true to be on. So that all will work. Alright, so let's just go ahead and boot this up. And then reboot it. So there's the last time. That would be a nice way to clear the terminal. Okay, same error. What do we got on LEDs? Now we got to look up which one is bit 0. Alright, so when you pull the SD card in and out, you can tell which bit that is, and they're aligned in a weird way. So I did not put enough filler zeros in there, by the way, but it still works. What, I put 2 in there? I need to put 3 in there. So this is down here, that's 3 bits, plus 3 is 6 bits, and 7 and 8. So yeah, this was why the LEDs looked wonky. Alright, so there we go. Make prog. And I'll assume it will build and everything will be fine, because, you know, all that code's perfect. Should double check. Yeah, okay, that went. We reprogrammed it. Let's do this. We reboot it. Okay, so now if I take the card out, that actually is doing the exact opposite of what I thought it was going to do. I wonder if I got it in it. We don't use the detect per se that I'm aware of, that I recall. Why are those other bits on? These 3 down here are going to be the, you know, the clock and the output and the select. Then there's supposed to be 3 bits of 1s. And it looks like I only have 1 bit of a 1, followed by 2 other values. And then these 2 bits on this end down there are going to be from this guy. So this down here is the line from the SD card out. And obviously the one that flashes is the card detect. How come these other 2 are on? The fact that those are on means I don't understand something simple. And let's fix the simple stuff before we worry about the hard stuff, because the simple stuff is usually what gets you in the way of the hard stuff. So who's the dingbat who blew this? 3 bits of 1s. Should it be 3 bits of LEDs off? 3 bit... Oh. 3 bits of 1s looks like that, you idiot. Proving once again that we have 0 extension when it aligns, when it sizes these values, which is a weird phenomenon. I was playing around with something along those lines the other day, and it was acting in a weird way. We'll get there soon enough. going back playing with other Verilog videos. Fine. Finally, I can actually boot it and get LEDs to do the right thing. We take the card out. Okay. Now, why does detect go on when the card comes out? That's because it goes to ground. Ground would normally light up the LED, but I thought I inverted it. Plug it in. A pull-up should cause it to go high, which would shut off the LED. So this suggests that the SD det signal is opposite of what I thought it was going to be, which then makes me wonder about other ones. So who inverted these things? Okay. What's going on with these? SD det. D out equals those values as they are. This one goes to the LED. No, boy, this is just nothing. I mean, nothing works the way it's supposed to work. So det A and B, who knows? Maybe I remember backwards. There's a mechanical switch in here. Maybe the switch closes when they shove the thing in, rather than when you pull it out. That's my story, and I'm sticking to it. So in other words, it actually is grounded, probably when you put the card in. All right, just saying. Let's go ahead and make this. Boy, I got to tell you, there have been times when I've wasted an insane amount of time with a justification like that. Let's go find the data sheet for this blasted card. This is so annoying. You know what? I don't need to. Let's measure it. Who cares what the data sheet says? Let's see what it really does. All right, where does det go? It's going to be some pin. IoT 192. Actually, the PCF. It's on pin 125. Those of you following along at home. Where is 125? Okay, it's right over here. It's right there. Be nice if we didn't short out all the pins. Okay, where are we at here? You put my scope on auto, and it is currently grounded. So that makes quite a lot of sense. Okay, now we take the card out, and it went high. Okay, in is ground. Okay, so it does have a switch inside it. When you put the card in there, it connects it to ground. It is as simple as that, okay? That's what the scope just told me. Oop, jeez, don't put this metal stuff short everything out. All right, now let us look at, let's cut a couple of probes out now. Let's get mean on this thing. All right, so I'm going to hook up to the card select and the clock. I'm going dual trace mode on the old Scoparoonie. Clock is 124, and the select is on a 117. All right, where is 117? 117 is right here. Normally I would connect the ground first, but I need to put these things all over the board. Is there ground over there? Yeah, but it's not. These are safe. I can sneak it in here because if I short these two pins, they're both grounded. As long as I choose that one right here, I'm good. Okay, yeah, that's safe. Is that one over there ground? Yes. All right, so this now is the card select. If I look at my scope, ooh, I saw a glitch. Oh, I'm so happy. Oh, we do have something going on there. Okay, let me get this thing triggered. The old scoper. It's ping 41. All right, so there is the chip select. Does go on for a little while and then turns back off. Now let's find the clock. 124. And it's right next to the ground pin over there. So we can sneak this booger right on there. Come on. There we go. There you go. And I see, I single trace it. Wow, I see something happening there. It's not what you want to have happen. It's ping 42. So the purple trace is the clock, and the yellow trace is the enable. So the clock isn't clocking, which means what? That means that the RAM switchover did not, probably didn't work. The fact that it works at all, okay, all right, let's think about this for a second. There was a mode where we put a lot of verbose dumping in the SD card driver, and we used to dump out in hex all the commands. But it's failing on just clocking. So we could still have a problem with the flash enable thing. It is possible. If there is a problem with the flash, what's happening right now, after it does this, it goes into a tight spin loop. And if that is the case, and it's running out of the SRAM, then we should see the chip enable on the SRAM going gonzo. And we should also see OE going gonzo. You're going to see OE going gonzo. Anyway, I think, if we put this in normal trigger mode, all right, yeah, so that's going nuts. That's the OE. Where is Mr. CE? If this is enabled and going nuts like the other one was, then, okay, so it is. So this is running and it's accessing the RAM for sure. Sanity check. It should not be writing because it's not calling any subroutines, and it shouldn't be. Yeah, this isn't doing anything. Put it on here. Yeah, nothing's happening there. This is definitely switched over. Yeah, that looks great. No, it's not going to have NMI, no. What's going on here? Right fee. We should not see any right at all. That's pegged off. We're seeing opcode fetching a la Modi. Okay, so this strongly suggests to me that the RAM got copied and that it's running out of RAM, and that, you know, it can access its variables, modify them, and use them. The fact that the clock is not going 1010 means to me that we may want to look more closely at how I/O operations work on the Z8S180, because it may be I'm decoding them wrong. Because it's possible that they don't work the same way. Maybe what we should do is go into a spin loop and hammer that port, that FE port, so we can look at it on the scope to see what's really going on. That's one test we could do. And you can also connect some of those signals that are inside the FPGA to all the unused pins and scope those. Anything to prevent the correct solution, which is to create a complete test bench for the whole thing. Oh, this is just funny. You know, if you do it right, you can create a test bench that will actually execute all the code and everything. But I don't want to simulate the whole CPU. Well, I've been on the horn here for quite a while. I think it's time for what we used to call a bio break in the office, and reconvene in a bit.